Study of pressure and pressure variations in the atmosphere is fundamental to an understanding of meteorology. The forces generated by horizontal pressure differences give rise to horizontal and vertical air movement, creating winds and clouds. The vertical variation of pressure gives us the ability to measure the height of an aircraft above a surface. The instrument that measures this variation is the altimeter. This lesson aims to give you an understanding of pressure in our atmosphere and its significance to us as aviators. What is atmospheric pressure? The air in the atmosphere is made up of molecules. The atmosphere therefore has mass, and under the force of gravity exerts a pressure on the Earth's surface. Put simply, the pressure of the atmosphere at any point is caused by the weight of the column of air above that point. Because the force of gravity is greater nearer the centre of the Earth, most of the mass of the atmosphere is contained in the lower layers near the Earth's surface. Consequently, air is denser and pressure is greater at the surface than at altitude. It is important to note that one of the properties of gases is that the pressure they are under is exerted in all directions. We will now look at how pressure is measured and represented in meteorology. The units commonly used to represent pressure are inches of mercury, millibars, or hectopascals. The standard unit being adopted is the hectopascal, but currently the millibar is still used in examinations. There are two types of instruments used to measure atmospheric pressure: the aneroid barometer and the mercury barometer. Changes in atmospheric pressure, that is, changes in the force or weight of the atmosphere, will either depress the mercury in the open reservoir and force more of the mercury up into the tube, or allow the pressure of the air in the tube above the column of mercury to force the liquid down the tube into the reservoir. This displacement is traditionally measured in inches. The higher the atmospheric pressure, the more mercury is pushed up inside the tube. The average height of a column of mercury that can be supported by the atmospheric pressure at mean sea level is 29.92 inches. This equates to 1013.25 millibars or hectopascals. The other type of barometer is non-liquid and is called an aneroid barometer. The aneroid barometer can be less accurate than mercury barometers, but is more sensitive to small changes in air pressure. An aneroid barometer measures the effective air pressure on a metal chamber from which part of the air has been removed. Changes in air pressure make the chamber expand or contract, moving a needle around a dial. The example shown here is an aneroid altimeter, which has a dial calibrated in feet, which may indicate height or altitude. Other types of aneroid barometers may be scaled in inches, millibars, or millimeters. Shown here is an example of a portable barometer used widely in aviation meteorology to measure pressure at the Earth's surface. Let us first analyze the variation of pressure horizontally. Why, for instance, might we get a high pressure in one area and a low pressure in another? If on a given day there is a greater amount of air overlying the surface, then the weight of air will increase, and therefore the pressure will increase. Conversely, if on a given day there is less air overlying a surface, then the weight of air will reduce, and the pressure will decrease. This gives rise to horizontal surface pressure variations, which are more commonly known as high and low pressures. Now we need to analyze how we might represent these horizontal pressure variations on a diagram. This is important because then we will be able to identify if one area on a surface is experiencing higher or lower pressure than another area. Because all surfaces are not at the same level, we need to reference our observations to a common horizontal level, usually mean sea level. This helps us see exactly what the true horizontal variation in pressure might be. How are these charts produced though? Looking at the diagram, we can see various stations reporting their particular mean sea level pressure values. If we now draw a line connecting all the areas with the same pressure, we end up with a pattern of lines over the surface. These lines are called isobars, and they join places of equal pressure. Using these pressure values, we can identify areas of low and high atmospheric pressure. Lower value isobars indicate a low pressure area. These systems can range from tens of nautical miles wide to hundreds and even 1,000 miles wide. High value isobars indicate an area of higher pressure. The isobars themselves can reveal a lot of information. A force exists that acts from the high pressure to the low pressure. This force is called the pressure gradient force, or PGF for short. The isobar spacing can tell us the relative strength of this force. This is important for wind speed analysis. Closely spaced isobars show a large change in the pressure and therefore a large pressure gradient force. This is common within low pressures. Widely spaced isobars show a small change in the pressure and therefore a small pressure gradient force. This is common within high pressures. Having worked through horizontal pressure variation, let's now look at how pressure varies vertically. Earlier on, we mentioned that pressure decreases with height in the atmosphere. In fact, it decreases at a decreasing rate. In other words, pressure falls very quickly with height near the surface, but at high altitude, the pressure falls much more slowly with height. This is because most of the air is located close to the Earth's surface. This is plain to see when the pressure levels are placed onto the diagram as shown here. However, pressure does not decrease everywhere at the same rate. This is because temperature affects the pressure lapse rate of the atmosphere. Cold air has a tendency to cause pressure to change more rapidly with height. Notice that the pressure lines contract towards the surface. Warm air, on the other hand, has a tendency to cause pressure to change more slowly with height. Notice that the pressure lines expand away from the surface. It is important that you understand this phenomenon because of its significance to altimetry. The altimeter is calibrated to ISA. This calibration assumes a pressure change with height in accordance with ISA. This is shown in the middle of the diagram. If the pressure were 300 hectopascals or millibars, the altimeter would register a height of 30,000 feet. However, if the atmosphere were colder than ISA, as shown on the left, the 300 millibar pressure value would be much lower than 30,000 feet. If the altimeter experiences a 300 millibar pressure, it will read 30,000 feet. The altimeter is clearly in error. The real height of the altimeter is much less than 30,000 feet. The altimeter is therefore overreading. If the air were warmer, as shown on the right, notice this time that the 300 millibar pressure would be found higher than 30,000 feet. At this pressure, the altimeter will register 30,000 feet, but it is clearly much higher than this. The altimeter is therefore underreading. In ISA, the pressure change with height at sea level is approximately 1 millibar for every 27 feet. But since pressure decreases at a decreasing rate, this does change with height. At 10,000 feet, the rate of pressure change is less, approximately 1 millibar change in pressure every 36 feet. For ease of calculations, we can say that the average change of pressure with height in the lower atmosphere is 1 millibar for every 30 feet. This value is useful to use in altimetry when pressure and height calculations need to be quantified. This ends the lesson on pressure. The significance of pressure variations horizontally and vertically will be better appreciated in the lessons on pressure systems, wind, and altimetry.